is a local, well, only sort of, a local San Francisco and Turkey startup. You know, it's usual relationship, right? The which how long are you guys lunch?
1.0 came out 2 years ago.
Okay, so 2 years ago, they have an office near here, you know, South of Market, and about a month ago at Postgres Conf in New York, the New York PostgreSQL conference, they released as open source a column store plugin for Postgres called CStore FTW, which is what they're going to talk about.
Yeah. I'm going to talk about a columnar store for Postgres. That's what the talk's about. And I'm Özgün Erdoğan. I'm one of the co-founders at Citus Data. Prior to Citus, I was a software engineer at Amazon.com in the distributed systems team. And at Citus, as Josh mentioned, we have 2 offices, one here in SF and another one back in Istanbul. For the columnar store, Hadi from our team in Istanbul did the bulk of the work. So that's that. And within this talk, I have about 30 slides. We also have a live demo for you guys to get to see how the whole thing works, gets together. And the slides are fairly technical, so you won't see polished slides. If you have any questions, technical questions throughout the talk, feel free to interrupt. And before I dive into the slides, the 30 slides themselves, I'm just going to spend 2 slides on talking about what Citus Data is, like a Citus DB, to put things into context. In one sentence, Citus DB is a scalable. Actually, before I start, how many of you guys have heard of Citus Data prior to this talk? Okay. And in one sentence, Citus DB is a scalable analytics database that extends PostgreSQL. So Citus shards your data, replicates your data, and when you send it a query, it automatically parallelizes that query across the cluster. And when we say extends PostgreSQL, I want to draw a clear distinction there, as in Citus isn't a fork of Postgres. So we didn't take a particular version of Postgres, say 8.0, 8.1, forked it off, kept forking it off, and then never looked back. In fact, before writing Citus, we looked into the integration points in PostgreSQL itself, the APIs that PostgreSQL provides. And you can almost think of it as, for the query planner and the query executor hooks, we figured, okay, these are good points to integrate, and then we almost built a scalable query execution engine for Postgres by using those hooks. So you can think of us more or less about like a PostgreSQL extension than a fork of PostgreSQL. So we started prototyping with like 8.4 and 9.0 into those APIs. With newer versions, we rebased to 9.1, 9.2, 9.3, rather than becoming a separate fork of PostgreSQL. For the end user, what that means is you get the new PostgreSQL features, you get native support for all the data types, for the contrib packages. People use HStore a whole lot with CitusDB. You get the extensions. Count distinct approximation extension is one extension that people are using. So you get the PostgreSQL experience, and we don't do anything for that. You just like load it into your cluster, and it just works. So that's slide 1 of 2 about what CitusDB is. A picture is worth 1,000 words. So this is the second slide. This is more or less the very high-level architecture. I have an example table in here, and then that example table is sharded into multiple shards. So all of these guys are like one of the shards within the CitusDB cluster. We have a worker node in here. I'll call this worker node 3. And then you can think of the worker node as an extended PostgreSQL. We have some user-defined functions for moving these shards around in the system. We have a few user-defined functions for creating the shards, and a few user-defined functions for repartitioning the shards on a different dimension for large table joins. So in a sense, you get PostgreSQL with a bunch of user-defined functions on the worker nodes. And the abstraction that we follow here is that we have a shard, and one shard maps to a single PostgreSQL table. So if you were to log into the worker node 3 and did a /t with pSQL, you'd see a bunch of PostgreSQL tables, each representing a distinct chunk of the table that we partitioned, that we sharded within the cluster. And we have a master node. The master node basically is also an extended PostgreSQL, again with the same theme. when you send the master node a query, the query executor, basically the distributed query executor, takes the query, parallelizes it, partitions it. So let's say you have a sum. It basically takes it and it converts that query into its commutative form to a bunch of different sums, pushes the computation to these worker nodes, like one per shard, executes the operation on each worker node, gets the intermediate results, merges them, and gives them back to the user. So basically, the extension in here is taking a query and converting that query into this distributed form to minimize the network I/O. That's what it does. And we don't keep any data on the master node. It's basically shard and shard placement metadata. So there is no data stored there. At a higher level, does that make sense? Any questions? So those are more or less my slides about what Citus does. And the talk. We have 5 sections in the talk. The first is like the motivation section. Why do customers want a columnar store? What's the motivation for using a columnar store? After motivating the talk, we have a live demo. We're going to do a live demo, like you're going to see C-store running in action. And then after the live demo, we're going to go back to the technical part. So as in, first, what's the file storage layout that we use for the columnar store? And it's an open file storage format, so we're going to talk about it. And then, 2, how did we integrate this into PostgreSQL? What were the decisions we made in integrating, and why did we make those decisions? And after the benefits section, then I'm going to conclude with some benchmark numbers. And the motivation section. So this is one of our customers coming to us, and this is their data. So they basically have a table of 30 million rows and 700 columns. So it's a fairly large table. And on this data, they're running simple SQL queries. So there is 1 or 2 aggregate functions, some filtering operations, some group by. So this is the typical SQL query that they're running on top of this data. And they're using a row-oriented store. So you can think of this as the dots are like 100 columns or like 200 columns each. So this is the data layout in a row-oriented store. When they run this previous query, for the row-oriented store to execute this query, it needs to go over each row, read each column, including all the hundreds of columns that are not in the query itself, and then give that back to the executor, and the executor takes that and does what it does, like the filter operations, the group bys, and the aggregations. So this is what that is. And the cost, obviously, here is, in the example, we had 700 columns. We ended up reading all of those 700 columns, but we only needed 5. If you went back to the SQL query, we were only using 5 of those columns. The data set size was about 40 gigs. So we ended up reading 39 gigs, actually more than 39 gigs of data that we didn't have to read. If you're using rotational disks, that's a lot of disk bandwidth. So you're reading all of this data from a rotational disk on your disk bandwidth. If you're using an SSD, which tends to give much better disk throughput, you're still spending about 60 seconds during the sequential scan reading data that you don't need to read. The database is still like spending all that time. And even if you're going to memory and you have a very high bandwidth there of 10 gigs per second, you're spending 3.94 seconds of just bringing the data from memory into the CPU itself. So that's a pretty expensive operation. Now let's go back to the same SQL query and look at the columns that we need to read. I marked them in blue in here. So we have the ID, we have the price, because we're doing a bunch of aggregate functions on that price. We have 2 filter operations, quantity and last pack date, and now we have a group by weight. So all in all, we have 5 columns. Now, when we execute this on a column-oriented store, and you can picture this as the ID column is laid out sequentially on disk, and then we have a size column that either follows that or it's either in a separate file. We read the ID column. We don't need to read anything from size. We just jump over to price and read the price column. We jump over, again, 200 columns or stuff, like we don't read any of that info. We read the quantity column and so forth. So basically what we're doing in here is, when you think of these guys as being sequentially laid out on disk, we're skipping the columns, hundreds of columns that we don't need to read. And that's more or less the motivation for the columnar store. Like 1, we're reading a subset of the columns to reduce the I/O bandwidth. This could be in memory, this could be on disk. the 99% of the data that we don't need to read. For this example, we don't read. And then because we're grouping columns of the same type together, say we have an integer column, the ID column in here was integers. Integers actually grouped together compress better. We have text groups together compresses better. We have timestamps, so we group those together, and then we get better compression. Within CStore FDW itself, we have PG-LZ compression, and the ability to actually include other compression mechanisms as well. So when you're writing to disk, you compress a group of values together. So by default, it's 10,000 values. So you write to disk less. It occupies less disk space. And when you read that back in, you're again reading back a compressed chunk of the data, not the entire data set. So that's the basic motivation. I guess now that we're motivated, let's do a demo, live demo, and then work on putting up the demo.
Yeah, just leave that out. Let's see what happens. So hopefully this goes well. I've had some disastrous live demos in my past, but confident this won't be.
We see it wouldn't be fun if it weren't for the risk.
And I guess in the meantime, any questions so far? Anything? Yep.
How does one end up with a table with 700 columns?
You'd be surprised.
That's not a bad design. I mean,
Data warehouse.
Yeah, actually, a couple of things. Yeah,
Corporate data warehouse.
Yeah.
Easy.
Like,
Yeah.
and there's a number of cases. Like, for example, imagine that the original source data came out of a spreadsheet. So each quarter is its own column for the last 25 years. It's only 100 columns.
So there's a big
Each month is its own column.
Yeah, there's a big batch of stuff in biology too.
Right. The other one that I've actually done this for is monitoring appliances. So imagine that you've got 300 or 400 or 600 sensors on a device, and each sensor has got its own on-off toggle. So you've got 700 Boolean columns.
or if you're just reporting a whole corporate chart of accounts, you could have hundreds of categories.
Also, the social networks, when you create an account with Yahoo or LinkedIn, now they're not using Postgres, but they pre-allocate like a couple of million columns for you right off the bat. Because they keep every click, everything you do is stored in that table. They're using that.
Yeah.
All right. Well, so as I was going to mention, my name's Ben Redmond. I'm a software developer at Citus, and I'm just going to give you a quick demo of how CStore works with Citus, and it's going to focus mainly on how to build and install it and use it, and then a brief sort of overview of some performance stuff. But Osman's going to dive into that more later.
I don't know if you can zoom the text at all.
I can.
Both for the people in the back of the room and for the people in our camera audience.
How is that? Is that better for people? Can people see that?
That is much better.
One more?
Much better.
There. Okay. Sorry. So, how many people out here have installed Postgres extensions before? Have you built something source and installed them, or used PGXN? Yeah? Okay, so what we're going to do is I'm going to start with sort of a Postgres extension that we've downloaded from source. If you have PGXN, there's actually easier ways to do this. It'll just handle it for you. But we distribute our extension both on PGXN and on GitHub. And so what I'm going to do here is this is an example of the GitHub repo locally here of our extension. You can see here just a bunch of files. And probably to install it, you first need to do, first step is to build it. The most common issue people run into when building Postgres extensions is that you need to make sure that it links properly against your Postgres installation. That means that typically it needs to have pgconfig on the path or something that you should read your make files, readme, or whatever, and figure out what's getting used to link into it. So for us, that's going to mean, oh yeah, now my stuff's just off the edge of the screen here. All right. Sadly, this display is not actually mirrored over on my side. Okay. So the first step is to basically, you can see here I've modified my path to make sure that the right pgconfig is on there. Then I'm going to build it. The only other thing you need to be aware of when using our extension is that it depends on protocol buffers. So you need to install that via whatever package manager you use. We have instructions for that on our website. So then once you've installed it, so that did all the linking. And now we're going to do the installation, which is just a make install target. Sorry. Okay, and so you can see here, this is actually putting it into the actual Postgres directory. Now I'm going to show you how we use it. So now that we've got it installed, we're going to start, and I've got here a demo DB directory. And so what I'm going to do is I'm going to run an initdb command to create a new direct DB in there. This will allocate a bunch of the other files, and then there's one step you need to do when installing our extension is to edit your Postgres config file to make sure that the shared libraries are preloaded. And this is because we hook into the copy command, basically, to allow you to easily and transparently load data into the foreign data wrapper. We need to be on the shared library load path. So you can see, oh, I was already there even. So you can see right here, you're just going to do something like this. That's all you need to do there. And then you're going to start up your DB. And so you can just use the example command here. Oh, not like that. Okay, so just tail our log file here, make sure everything looks good. So that looks good. So now we're going to connect. Okay, so now we've got a regular Postgres PSQL session. And the first step is going to be just to run this create extension command, and this is what you run.
And thank you for using the 9.4 development.
Yeah, I noticed that.
So we got a little live testing.
So, I think that's yeah. This is actually my cobbled together version of the 9.4 development server, where I was trying to backport parts of JSONB in there, but did not work. But it works enough for this. So you can create your CStore FPW extension. This will just initialize a bunch of the resources related to the extension. Then the next step in any sort of extension creation is going to be creating the server. And the server is a concept that is, sorry, not any extension, any foreign data wrapper. And this is basically, you can think of as shared resources for that user related to the foreign data wrapper. For us, there's not a lot of stuff that happens here.
Yeah, although I was talking about having the server relate to a directory location.
Yeah, if you had that type of stuff.
Which might happen in a future release of CStore FPW.
And so there, now we've created our server, and now comes the exciting part, where we actually create a table that uses it. And so you can see, actually, I'm going to do this example here. I'm going to use the TBCH data, which I was going to talk more about. This is a popular benchmarking suite, basically. Oh, not paste well. Okay, there we go. And so as you can see, sort of, we say create foreign table. That sort of references that it's coming from the foreign data wrapper. Then we've got a regular schema that looks like anything else. Then we specify the server down here. So if you had multiple servers, you could change it there. And then on the foreign data wrapper, there's sort of options that are specific to each one. And so for us, there's only two options. There's the file name, which is where it's going to create it. So you can see here, this is just a directory on our host. And then the compression option. The compression option has two possible values. There's none, and there's PGLZ, which says Postgres is built-in compression type. So we're going to use a compress table at that location. So now we've got that data in there. So now to load data in, we're just going to use the copy command that you see here. So I'm actually just going to load in a small sample of data because this stuff actually takes time to load. And we'll just show you that live so you actually trust that it gets loaded. And so there, we just loaded in 1,000 rows. And then we can do things like from line item and completely unreadable. So we'll change it over to expanded mode. And they're still too wide for this display, but you get some idea that there's data in there and that works. And sort of like any good TV chef here, I've actually got a pre-cooked version of this DB that I'll show you with like a gigabyte of the same data loaded in. And we'll just do a quick performance comparison and sort of, it's going to have the same data loaded into a Postgres table, loaded into a CStore foreign data wrapper, just on a single node, and then we're going to show an example of it running on a Citus cluster just on this one host, basically, the 2 nodes on here, using CStore there as well. So because we work with Postgres, you can just install extensions, and CStore is just another extension. So I'm just going to shut down this database. And then I am going to start up the next one here. Okay. And we should just be able to connect to it. This. Awesome, I can't believe this is all working. All right. Okay, so, and now I'm going to show you a simple query. So this is actually a query from TPCH. This is query number 3. And so we'll run it, and we have timing on, and we'll just look at the responsiveness between each of these guys here. So this is the query just running against our Postgres version of the table. And so you can see here, this will run. Usually it takes about 6 seconds. Although I'm not plugged into power now, God knows what happens with the power saving features on here. And so we'll run it just a couple times to let stuff get in memory or not, depending. I have sort of weird behaviors with buffer management on here with the Postgres version of the table. But so you can see there sort of 6 seconds basically for that. And now if you run D here, you'll see actually here the output. These are the 3 tables that we have here. These all contain the same data. So we just use the Postgres line item table, which is a regular table. And then we have 2 that are foreign table types. And one of those is just using CStore. So this is just an example with a gigabyte of the same data in the CStore table. So we'll just go up here. We'll change this to CStore. Otherwise, query remains the same. And so now we're reading it off of a columnar format with compression enabled. And you can see we get down to sort of under 4.8 seconds, and we'll see what happens here if we get more into RAM, if it improves, and down to 3.8. And then, so that's like, actually, that's even better than came out before. I had the numbers in my head for percentage reduction, so that's like around 35% probably. And so then we can see the difference here from using CitusDB with CStore, which I think is this table name. And so this should be even faster because we get to leverage the same columnar storage format, but we get to do it in parallel. So now we're down to 3 seconds, and we'll run it once more, and I bet we'll get even lower here. Yeah, so 2.5 seconds. And so that's just from sort of combining the 2 improvements that we sort of have worked on for Postgres. So now I'm going to hand it back to Ozgun.
So that's the parallelism, right? It's really like
so right now we've got actually, on this one node, we've got 4 different shards running across 2 servers. And we're querying those as well.
And that's a gig of data?
A gig of data, yeah. It's the same data set in each of the tables.
And I think if we had set the type for this.
Oh, here. You actually want to show the other sort of dramatic thing is do a PG total relation size in the Postgres table, and then show the file size in the CStore.
Is it underscores?
Yes, PG total relation size.
Wait a second, let me kill it.
You have wraparound problems.
Yeah, I am. Oh. Okay, a second. We'll go into them. Said total relation size?
Yeah. No, it doesn't work with CStore. That's what the Postgres table.
Oh, okay, okay.
On the file.
It will show a 0 on the CStore table
Okay.
because it's a foreign table.
You probably ought to fix that.
Okay. Oh, there's a.
Okay, I
function
wrapped that
for
in
this.
PG
Yeah,
size
yeah.
pretty.
By the way, you're also showing one of the really awesome features in 9.4, which is the borders around your PC.
Which I think I stole that from maybe your poster on customizing your PSQL RC, but okay. Yeah, so we've got there like 903. And let's just see here. I think I've got it. Yes, this is, I think, God, I'm trying to remember where this file lives now. I think it's in test resources, I think. No, that's the not-baked one. Let's see. Yeah, here we are. This is the CStore version of the same table. So you can see here, this is roughly 250 megabytes of data.
Yeah.
Yeah, and so that's, your compression rates will vary, obviously, in production, but this is, TPCH is meant to be a representative data set that gets generated.
Yeah. I did one where the columns were basically all numerical, and it compressed down a lot better. It, in fact, compressed down 94%.
Oh, wow. Yeah,
So-
that's great.
That's about typical for American columns.
Yeah.
Did anyone else have any questions before I hand it back over to Ozgun?
What level of parallelism are you able to use effectively?
Depends what your hardware layout's like.
Well, I think for Intel using that box,
Yeah, I mean, we've definitely used 8 in parallel. We often have more. Like, we will run
8-0.
8. Sorry,
8-0.
8-0. We haven't run anything that large
On that
on
scale?
single nodes, but
Yeah.
we've run it across multiple nodes with 80 parallel tasks.
It's basically how much PostgreSQL can run those independent queries in parallel. That's what it comes down to.
Yeah.
And the bottleneck that we run into is if you're running on a single machine, even when you have different tables, there is a contention around the buffer eviction lock. That's the contention that we run into. It's not, yeah.
That's mainly if you're just a memory bound workload.
Yeah.
But yeah, we've run 80 across multiple machines, but I don't think we have any customers with 80.
Yeah,
CPUs right now.
I think for C-store, since in that architectural diagram that we looked at, each shard is one PostgreSQL table, and that one PostgreSQL table in our architectural diagram is going to be one C-store table. We'll be effectively able to read independently across all these tables, so I would expect it to scale fairly well. Just
So we
as-
bypass
Yeah.
that buffer
Yeah,
management
you're
stuff,
separate
basically.
Yeah, because
Yeah.
there is no buffer management, they're just independent tables, and I would be reading it from the C-store files. So I would expect it to go really well, but then you never know with like 80 cores. Like that has to haven't yet run.
Any other? I think I saw a couple others. Yeah.
Yeah, so
Why don't you get plugged in?
Yeah,
sure.
you focused a lot on read access. What kind of write performance do we suffer with?
Do you get access to go with your super fast read?
Well, I'm asking the expert.
Depends whether you have compression enabled or not, is one thing. So that's probably the biggest contributor. Is right now we're using the built-in Postgres compression formats. It's pluggable, so you could plug in your own functions. We haven't done that yet. We know the levels of compression that Postgres uses is not as fast as the other ones. We haven't benchmarked it. I can definitely tell you it's not as fast as a copy into a regular Postgres table. Yeah, it hasn't been a priority for us.
Well, the other important thing to know is that currently the only way to write to C-store is copy.
Yeah.
There's no insert update delete.
I see.
Yeah, although realistically, we'll probably do multi-insert. Doing multi-insert makes sense. But any sort of single row update would be
It's
a little
it's rarer
crazy.
in column stores. Yeah.
Yeah.
Yeah. Any other questions?
Have you done a comparison of the column store and just the index, creating index using those sub-columns?
So column stores probably, we've done, I don't know if we've done any in-depth comparisons. I was going to talk about the indexing features that we have in our C-store. A lot of our users that use this use it for large analytic queries or for a large portion of the database or table where indices aren't as useful. But we haven't done, I was going to talk about the indexing support that we do have.
What's the license? Are you released it as a Postgres license or the extension?
This is released under the Apache license.
Yeah. All right.
So is there any work being done on packaging this? Using compiling or using PGXN is not possible in some environments because of restrictions on internet access, compilers on the service and server. Is there any work being done to package this?
What do you mean by, like into?
Like as an RPM or a dev?
Not actively, but something we could look at. I mean, the source code is on GitHub. You can
that's the
download
only thing that's
that.
kept me from working on it so far.
Okay.
I've looked into it, but it's like the only place I can put it is on our build box because we don't have an environment that we can
Okay.
use for.
Well, we should talk afterwards. We can figure something out, I'm sure. All right. I'll hand it back over to Austin.
And going back to the technical side of things, the design decisions, the architectural decisions, before we started working on the columnar store, we actually wanted to get a picture of the landscape. What are other people doing about columnar stores? And how are they doing it? And when we looked at like the trends, what people were doing, we grouped them into 3. One is you take up a database, and then you fork it off, and then you implement your own storage engine. You keep doing your changes to your own storage engine, and you don't look back. So that was trend number 1, and it becomes its own self-contained solution. Trend number 2 was on the Hadoop side of things. So there's been a fair amount of work done on Hadoop, specifically the Hadoop Distributed File System, HDFS, to come up with a columnar store, because people were writing a lot of data into HDFS, so they want to write less. And they're reading a lot of data from HDFS using MapReduce or other query execution primitives, and they want to read less. So there was work done on the Hadoop side of things, and it was open work. And they were actually making progress on the file specifications. So that was one interesting thread, essentially. What are these people doing on the Hadoop side of things? And on the PostgreSQL extension side, with the new PostgreSQL extension machinery, the foreign data wrappers, there were different approaches to it. One is basically you have your own columnar store. This could be MongoDB. This could be your commercial database. And then you'd be writing a foreign data wrapper that connects to that columnar store. When a query comes in, you go and read the data from the columnar store and you give it back to the PostgreSQL. So that was like the third approach that we've seen. And what we did is we basically took the best of approach number 2 and number 3, and we combined it together because we wanted this to be easily usable with PostgreSQL. We wanted to support all PostgreSQL data types, give you the same experience. At the same time, we wanted it to be self-contained, not have external dependencies to external databases. So we figured, okay, let's get number 2 and number 3 and make a columnar store with the best of these two approaches. So I'll start with the approach number 2, which is the columnar store file layout, the columnar store specification. And rewinding back a couple of years, the work that came out of the Hadoop side of things, the stuff that was published and that was specified out there, probably the first popular columnar format in the Hadoop side is the RC file. This is joint work between Facebook and Ohio State University. And their idea is basically if you have 100 million rows, 100 million records, one way to lay that out is you do 100 million records of column A, 100 million records of column B, 100 million records of column C. What these guys do is they first do a horizontal partitioning. So they say, let's get 1 million records of column A, and then let's put a million records of column B, 1 million records of column C, and another million records of column A. So they do one horizontal partitioning, and then they lay out the columns that way. This work came out. It was published in 2011 on ICDE. In the paper, they have a paper. They talk about their motivation for picking this up, like why they went with this, and then compare it to the different other approaches. They also give a performance evaluation of it, like how does this approach compare to the other approaches. So that's the paper, and then once Facebook picked it up, and then other people started picking it up, it was integrated into Hive. Hive started using it. This is one of the other Hadoop projects, and into PIC. So it became quite popular pretty fast because there was a need for it. Then, a few years later, actually, as recent as last year, there was a second generation of the RC file called the optimized RC file, or the ORC file format. Like that's the specification. And the primary difference between this guy, which superseded the RC file, is actually those two features. One is they have skip indexes. To your point, small skip indexes within the file itself. So when you run a query, they look at small min and max values to skip over a bunch of values or not. So that was the lightweight indexes. So they're using skip indexes to skip over unrelated columns and rows. And then they enable different compression methods within the same file. So if you have your column A, you could use gzip for compressing your column A's data, and then for your column B, you could use snappy or some other compression methods. So you could use different compression methods within the same file. So these two were the improvements. Before I dive into the specification itself, I have a diagram coming up, repeating the org file layout benefits. One is the columnar layout. So org groups column values together and then compresses them to get decent compression benefits. And then the third part is the skip indexes. So skipping over unrelated values, values that are unrelated to the query. Any questions at higher level?
So for these kinds of data, you need something that has total ordering, the data type?
Mm-hmm. For the skip index to be useful, yes, I'll touch into that in a couple of slides. One is if your data has an inherent time dimension to it, say your events table, your facts table, so the data is coming in, it has some time dimension to it, and your queries actually are going at that time, they become useful. Another approach is, which is what I've heard they do at Facebook, basically they sort the data before loading it in. So they import an order as they're loading in the data, that way they become useful. But yes, The other part is you can combine different skip indexes together. So if your query has 5 skip indexes, you look at the ANDed version of all of those 5 filter clauses. And this is the summary of the benefits. I'll dive into the specification itself. This is mostly more or less a copy-paste from the org file website. So this is the layout. And then on the left here, you see the stripes. Those are in CStore, the config value is 150K rows are grouped into a single stripe. At the beginning of the stripe, you have your index data. So these are the lightweight indexes. So say your query is going over column 2 and column 4. You look at the index data and you immediately jump offsets for column 2 and column 4 and only read those columns. So you actually skip over the columns you don't need to read. The index data also keeps these min-max values that I just mentioned. I'll get to that in a sec. So it has that. And they're lightweight. They're small enough. They're actually pretty tiny, such that they always more or less fit into memory. So when you're running queries over your CStore data or your org data, that stuff is always in memory, so you can easily skip over the data that you don't need to read. Like you don't go to disk, so they're pretty tiny that way. So those are the indexes. They're like, again, small. Then you have the actual data itself. These are the records or the tuples. And you have 150K of these here grouped together. That's the. And these guys are laid out sequentially by column. So your first column appears in a file. Your second column actually appears after the first, the third, and fourth. So these guys are all laid sequentially on file. And there is another level of indirection here, which is basically each column, and by default that would have 150K values within it, is split into blocks. So we have 10,000 column values per block. There would have been 15 of these guys in here. Didn't notice in my slides. And so you have 10K together, and CStore and org actually compresses these guys together. So that's what happens in here. And then the min-max indexes that I mentioned for the column values in here, for the 10,000 column values here, we keep the min and the max values within these index data. That way, when you have a query with a filter clause in it, you can actually look at the min-max values and then skip over, say, block number 1, block number 3, 4, and 5, because we don't need to read that information. So that's a basic layout. Any questions or?
Does it handle delete and update?
Not at the moment, no. This is append only as it stands on GitHub today. The deletes would go, there are different ways to do deletes, so I'll touch to that at the end, and then we have some issues and workarounds on the GitHub page. But as it stands today, native deletes, if you did a delete, it would say I don't support a delete. There's other way to drop data or delete data.
So we're saying that if I know I'm going to actually be filtering on a column a lot, I should actually sort the source data by the before copying it into a CStore table?
If you are going to do filter operations, if your queries, for example, are going to have, say you're doing user ID, and now user ID is equal to 100.
Yeah.
For example, that's, then if you sort on the user ID dimension, the data before you load it in, then these guys, because they're sorted like for each block, the skip indexes in there will contain, say, user ID 1 to 1,000, user ID 1,000 to 2,000, and then they're going to filter out the blocks that aren't relevant to the user ID lookup you're doing. This isn't exactly like a PostgreSQL database where you just can fetch a single row, but if you're, it's not the exact same thing, but then it helps a lot. And one last thing about the index data that Ben briefly touched upon is that the org specification used protocol buffers to keep the index data. The motivation behind there is being backwards compatible. If you're adding new stuff into your indexes, your sums or other statistics about the data, then their protocol buffers gives you a nice way to be backwards compatible. And then that's why we picked up protocol buffers in CStore FTW. We use protocol buffers just for this data. That's like another detail.
So if I understood the indexing, you really have one ordering, and it's like a key sequence table. You only get to sort on one thing. It's not like multiple indexes. It's okay. It's fine. I just wanted to make sure I understood.
Yeah, you could actually,
Because because otherwise you wouldn't know which column went.
Yeah. And then, so that's the columnar layout, the org specification of the layout columns. And then there is something to be said about compression itself too. The default compression algorithm in C-Store FTW is PGLZ. This is what PostgreSQL uses as well for toasted values. And then for the toasted values, one difference is you take the toasted value, you call PGLZ, and then you do the compress, decompress. C-Store FTW does call PGLZ on 10,000 values together. So that's, but it does call PostgreSQL cores, and then that's the default compression algorithm in there. One thing that I love about C-Store FTW is pretty easy to add the compression methods. In fact, if you have a particular case, let's say you're doing a CPU disk trade-off, you have SSDs, and you want to get more bang for the buck on your SSDs. You want to benefit from storage side of things. Or if you have rotational disks and you want to take on your disk I/O, you can easily swap in your own compression algorithm, gzip, bzip2, whatever that is, making that CPU to disk trade. Like you could say, I have enough CPU cycles to spare, so I'll just use a better compression algorithm. It could go the other way too. You could just snap one of the cheapest on CPU compression algorithms. It's pretty easy to swap that in. And for C-Store FTW, you can use for completeness different compression methods at the column block level that we just see. Now, this as it stands is all cool, the fact that you can use different compression methods, but the question is how well does the default compression algorithm that comes with PostgreSQL, where we compare 10K values together. These are the numbers from the TPCH benchmark, again. And the TPCH benchmark is 10 to 20 columns, and then in each column you either have an integer, a timestamp, text, so it's a mix of all of these different types. The biggest table is the line item table. That's your events or your facts table. The other things in here, I normalize the table size 1 to show the different compression ratios in between the different tables. And then you get more or less a compression ratio of 3 to 4x with this TPCH benchmark. So this guy was 9.1 gigs. I believe it tracked down to about 2.4, 2.5, 2.4 gigs. And it's more or less the same across the different tables. The question is obviously it compresses by 3 to 4x. What does that get to the end user or the end customer? And the answer is it depends. If you're in memory, if your data is in memory, then you basically get more effective memory usage. So if you have 2 gigs of RAM on a machine, you can fit a working set of 6 to 8 gigs onto this machine. So for in-memory workloads, you get more effective memory. That's the primary benefit. If you're on SSDs, chances are your SSDs are somewhat expensive, about 2 terabyte disk, and this way you can increase the effective disk utilization on your SSD. So from 2 gigs, they go up to 2 terabytes. If that's your disk, they go up to 6 terabytes or 8 terabytes. So you get the SSD benefits, the storage benefits. Yeah.
So I was wondering, when you have a compressed memory, though, doesn't that you take a CPU hit?
You take some CPU hit, and then
what percentage? How much?
Well, not a whole lot, as it turns out.
I was doing some testing against my own data sets with stuff that fit in memory, both in the regular Postgres table and in the compressed C-Store table, and it was a wash, actually. So even if it fits in memory, the fact that you're using less memory is enough of the benefit on queries that are hitting lots of rows that it erases any extra CPU time it takes.
Another way to say that is that the equation is changing about the relative performance metric of a CPU versus I/O, and the CPU has become an extraordinarily inexpensive resource, even over a small delta time of a few years change. The speed of increase of I/O has not kept pace with CPU performance improvements.
And yeah, going back to the benefits for use case, if you're using SSDs, you have the benefit of, yeah, sure.
Yeah, so at what point if you uncompress?
This is, if we look up the indexes, we say these are the column, So this is the block you want to read, and then this is the block that you want to read. We're going to read that block and we're going to decompress that block. So we compress at the block level and we decompress at the block level.
So, sorry, I'm not familiar with PGL compression. So my question is that compressed sortable. So you can compare compressed value, like in predicate.
Oh, that would be predicate filtering would happen here. So that min and max values would live in the index data. So when you send in a query, and I'll touch upon that in a second, we basically look up at that index data, and now we decide, okay, these are the columns that we're going to read, and that these are the blocks that we're going to read. So this is just the data stuff. The index live here in uncompressed form. Like the min and max values, when I index the min and max values live here on the index data section in uncompressed form.
Okay, so every time a block is being read, as soon as it's being read in memory, it's that one.
Yes, the block is read in compressed form and then uncompressed, yeah. Going back to the compression slide. So in-memory benefit is effective memory usage increases. SSD benefit is you get more bang for the buck. Your SSD storage increases. If you are using rotational disks, chances are you're bottlenecked on your disk I/O. And if you're like this guy who's 100 megabytes per second, this is like a commodity disk, your effective disk I/O then becomes 300 megs or 400 megs per second because you're reading the data in compressed form and now you're decompressing chunks of it. Another benefit is obviously if you have a single machine, you probably don't care about the cost of having the rotation disk. But if you have a cluster, let's say that stores a petabyte of data, and you have 300 machines to store that data, they're beefy on the storage side, then compressing by a factor of 3 to 4x reduces the cluster size from 300 down to 100. So you get that benefit too for the large big data use cases. So this is the compression part. That was column layout compression and then the skip indexes. Basically, for each column block for time k values, C-store saves min and max values in a skip index. That was the index that we've seen there. When the user runs a query, we extract all filter clauses from the query. And in the previous SQL that we looked at, let's say quantity greater than 100 would be filter clause 1, and then stock date, last stock date is down 2013, 1001 will be filter clause 2. So we extract those two filter clauses. And we basically go and apply PostgreSQL's constraint exclusion mechanism. This is the part that I love about it, in that we could have however many types we want, and now we basically create a constraint, and now we apply a constraint for those filter clauses. We then compare those constraints against the min and max values. That way, without really writing I wouldn't say a single line of code, is like basically a function. We create that constraint and apply that constraint for any data type that PostgreSQL supports, which is very exciting to me, because if you see what the other guys are doing, this is just like a function, and then it just works. So we apply PostgreSQL's constraint exclusion mechanism. Now, what that effectively means is, as we discussed, is this is useful if your input data has an inherent measurement. That's like one, because the data is coming somewhat ordered, and then you're looking at a particular subset of the data. Or you could sort the data on one dimension, and you could load it that way. And now you'd be benefiting from skip indexes. So the three benefits then of org file format are the columnar storage, the compression, and the skip indexes. Are there any drawbacks? And looking at this from a PostgreSQL user standpoint, one drawback is if you look at org, they have integer, double, boolean, text, timestamp, and maybe a few other data types, and then that's all there is. And there is no type system within org or within the whole side of things. So each data type needs to have a separate call path to handle that data for constraint exclusion, for keeping statistics. And that's not something we wanted for the PostgreSQL users. We wanted to support all the data types. There are like, I think, about 40 data types within Postgres. And we wanted to support the data types that come with other packages, again, sort of an example, or new data types that users could write. So that was like one decision criteria for us. The other part is because this is work done on HDFS, a file system, there isn't much of a notion of like joining different files together. So there is no statistics collection or no such machinery within the org file specification, which is cool if you're reading files, but if you're joining tables together, you want to gather statistics. So I'll touch upon the type part if there are no questions. So I'll go with how we did the data types, and now we basically just use PostgreSQL data types. That's the short answer. This is a code segment. It's a protocol buffer declaration, not super readable, so I'll read it for you guys. The left-hand side is the org file specification, which is their protocol buffer type, and then these are their statistics. So you have an integer statistic here, and now you have int64 minimum, int64 maximum. You have a double statistic in here, which is the double minimum, double maximum. String statistic, string minimum, string maximum, and so forth. So the idea is whenever you have a new data type that you want to use with org, you write another one of these guys, you put it here, for org to support that data type. And not only that, you write a bunch of functions to do predicate filtering, like that constraint exclusion machinery for that data type itself, which is a fair amount of work and doesn't fly where you are trying to support a lot of data types. The right-hand side is what's there in the C-store ATW for all the data types there is. It's a byte min value and a byte maximum value, and then this is basically the PostgreSQL's type system has this nice abstraction, which is like a datum type. Datum represents all data types available in PostgreSQL. So we basically use the PostgreSQL data type data representation. And then all of this actually goes away on a type basis. You just have this. And then we don't need to do any extra work for constraint exclusion. We get to support user-defined types as well. Like if you have an input-output function, that support is free, so we don't need to write any code. And the other nice thing, which ends up being a performance improvement, is because we're using the PostgreSQL datum type, we don't pay any deserialization overhead. We don't need to take a particular integer, convert it into PostgreSQL's datum type. We basically write it as a datum, and then when the query comes over, we basically take that datum and then give it to the PostgreSQL executor. So there is no deserialization overhead. It goes pretty fast. So that's the different data types. And there's a statistics collection part. Actually, when I was writing up this slide, I somehow ended up going back to our Hacker News announcement for columnar store. And one comment that I read there, coming from the Hadoop side of things, is we've looked into C-store, and you don't actually do any statistics collection. You don't even have simple counts. And for someone who's coming from that side, looking into the code, that's true. It doesn't look like the fact is the foreign data wrappers have a very nice API. And then you basically implement that API. When the user runs analyze, you need to run it manually. That API collects random samples from the data. So we collect a random sample, and we give that random sample to PostgreSQL. PostgreSQL then goes and constructs histograms, distinct counts, most common value frequencies, and all kinds of other stats, and puts that into PGStat. C-store is on PGStat, and basically estimates query cost for different query plans. And then so we give that back to PostgreSQL, and PostgreSQL picks the best query plan there. I have an asterisk there because the work that we're doing on the query cost estimation is not complete. It's an ongoing work. It does much better than the default one, but that's something we're looking to improve. Now, for the end user, what does that mean? It means, let's say you set your work map in PostgreSQL for your group operations, for your order by operations. PostgreSQL will make sure that that setting that you used will be respected, because we get informed resource usage. That's like benefit one. The second benefit is if you have table joins, then because we do the cost estimation here, PostgreSQL is going to pick the best join order and the best join method. So that's the other benefit. And then the type system and the statistics collection are the benefits of using PostgreSQL and the PostgreSQL foreign data wrapper APIs. And on to the benchmarks. I guess before I dive into the benchmarks, any questions?
So this would bias your joins toward sort of merge joins, I think it.
Depends on how we estimate the cost. I think we do have a bias in our current cost estimation, as in if we, because all of this data lives in stats, we look at the filters and we look at the projections, and then based on that, for the access paths, we pick a cost. I could go back to the code, because in the code it says right now the way we're doing it actually has a bias for this join method, as you said. I don't remember which one. But that's what we're looking to improve. That's actually to remove that bias when we're doing the join order selection. After the talk, when I switch out from the presentation, I'll take a look and then I'll tell you which one we have a bias for. And recent benchmark results. Again, Hadi from our team has been gathering benchmark results last week, and actually he's gathering benchmark results now. So this is just fresh data. And then we use the TPCH standard benchmark. So it's an industry standard decision support benchmark. To be honest, it's not the best benchmark for this, just because we have 10 to 20 columns in TPCH data, whereas with the customer data, we end up having 100 columns or 200 columns or 700 columns. So it doesn't favor us or the columnar store in any way. But it's a standard, so we went with the standard. And we did in-memory, SSD, and rotational disk numbers on 10 gigs of data on EC2. We compared vanilla Postgres, C-store uncompressed, and C-store with compression. First, starting with the rotational disk numbers. So this is a rotational disk. And before I dive into them, long parentheses, just an important parenthesis. In these benchmarks, we ran one PostgreSQL query after the other. So we only use one CPU core. Underneath the covers, we're using the entire disk bandwidth available. So in these numbers, we're utilizing the entire disk bandwidth, which is a bottleneck that compressed C-store is removing, but we're only using one CPU core. If we had SciTOS-DB, for example, on this machine, or if you were running multiple queries together, then we'd be using more CPU in parallel, and then the relative difference between regular Postgres and then C-store would increase. Does that make sense? Like that, this query in here is bottlenecked on CPU, but now we have many CPU cores available to us. We only have one disk. All parentheses, basically. TPCH benchmark representative sample set. All the other queries are more or less the same, so you just pick some. And then we drop the caches before running queries, so this is all coming from disk. The query.
The other queries are not shown here. You don't know, like,
which one?
So there are 21 queries.
There are 22 queries.
22 queries.
So we only
not
pick.
Shown here. Did not improve or?
No. You can't consider representative set. And now when you look at your representative set, you're going to see they're all like 75 seconds. Some of the queries are like way up there, some of the queries are there, like down there. The relative difference is more or less the same. It's just that if I picked up 22 queries in here, that occupies the space, that's one. Two is we're also running comparisons against SciTOS-DB, so these are most of the queries SciTOS-DB currently parallelizes, but you can think of these numbers as being representative, and the ratios again being as representative. It was mostly for aesthetic purposes that we picked the subset in here.
So how did query 1 do?
Yeah, query 1 would be the most interesting.
It is. I could put it there. When I put query number 1, so for query number 1, because it's only computation while I'm reading columns, there is that much of a difference. And I'm still going to put it, what ends up happening at query number 1 is, it's the slowest of all queries. This chart just like explodes, like goes up all the way, and all the other numbers shrink. So to the end user, it looks as if there's only one query and everything else like at a smaller scale. So that's why query number 1, for query number 1, because it's aggregation based, the runtimes are more or less the same. But the reason I didn't in here, for example, query number 19 is something similar, is not because they're similar, it's more like the chart just goes where they can, and then you only see query number 1 and not their guys. Does that? Yeah. Okay, cool. And on average, if you actually average out all the numbers and view the averages, the benefit, and this is the store engine better runtimes, and on the orange ones are C-store compressed. The benefit averages out to be about 2x when you're using a single CPU core. When you use multiple CPU cores, we'd expect them to be higher, and we're working on numbers, on getting numbers that show that they're higher. So that's the rotational disk. When you go over to SSTs, both the total execution time reduces significantly, and the difference between the blue lines, which is regular search engine, and the orange ones actually drop too. Just because with SSTs you get much higher sequential read throughput, so the difference goes from on average 2x down 40%. That's what you, again, this is on a single CPU, and you have an entire disk available to you. And just to put that into context in terms of the amount of disk I/O saved, we also ran I/O top while running these queries to see how much disk I/O was being issued for each query. And then there obviously the number is more dramatic. Like if you look into these queries, for query number 6, we read 9 gigs of like we're doing a scan, and then query number 6 is like we 9 gigabytes of data while it's executing. Whereas if you look at C-store compressed, there is about 10x improvement, I think 11x. It drops from 9 gigs down to 0.8 gigs. So there's a major reduction in the amount of I/O that we reach this. And the more CPU you have, the more you're going to get benefits out of it. So that's the total disk I/O savings. And now for completeness, these are the in-memory numbers. And there, when we are going in memory, the benefit shrinks even more, like in here, just because then basically CPU bottlenecked on the CPU. So you're reading the data in memory. There is some benefit to using C-store. Now that there is some overhead in using compression, because what you're seeing here is because we're decompressing the data as we're reading it, it introduces some overhead, not a whole lot of overhead in this particular scenario. And then the data is coming from memory. There are two things in here. In this particular use case, I think there is some benefit, and then there is some overhead of compression. The implicit benefit is that your effective memory size is increasing. So this was on a machine with 15 gigs of RAM. If we had data that totaled 30 gigs, we'd still be answering these queries from in-memory, because they would compress and they would fit into memory onto this instance. The second question is, I guess, can we make these numbers go better? For columnar stores, there's a new trend of doing vectorized query execution, which is now that we're reading columns and columns together, the actual follow-up is instead of having to go over the state one row at a time of PostgreSQL, having a different executor hook. And then that executor hook reading 10,000 values all at once.
I mean, for what it's worth, we've already started work on having push-down aggregates for Postgres 9.5 as part of the standard for now represent. It just won't come until, I guess, 2015. So.
Yeah. And and then it's also we need to write for the vector execution with pushdown basically new aggregate functions, because the aggregate functions, like there is some effort involved, actually a good chunk of effort involved in when we write an aggregate function. The aggregate functions today take one value and then the next value and the next value. They would need to change, so we need to have aggregate functions for some bounds and all operators. So instead of taking one value at a time, they take all values, say 10,000 values at one time and what they need to. But there is definitely work that can be done here. It's not done yet, like for vectorized query execution, just as, which is, speaking of work to be done, comes over to future work. And I guess C-store is an open source project. The code is available on GitHub. It's actively run. And then we have issues open, we have enhancement requests open, so it's all there. Some of the enhancement requests and stuff that we're thinking about is listed here in particular order. Improving memory usage, automatically determining paths so that user doesn't have to deal with it for usability purposes. Natively insert update support. This came with PostgreSQL 9.3 API, so actually having that sort. Improving read query performance. This could be vectorized execution, this could be other things. Different compression methods. This is an easy one. Like it's actually pretty easy to implement different compression methods. Bug fixes, better cost estimates for table joins, and many more. We'd encourage you to go to our website if you have a use case for it. Look at the project, try it out. If you have any feedback, if there's one thing or two things that would make it for you, just give us feedback. Because we're looking at these features, and we're looking at the demand for the features. We're looking at also implementing the features, and we're prioritizing them accordingly. Okay, and then the summary is basically C-store FTW is an open source columnar store for Postgres. It's there. For the data layout, we used ORC, the second generation RC file format, which gives us columnar data, different compression codecs, and skip indexes. We integrated that into SQL using the for-way and array APIs. I think those APIs are very powerful, and that's how I feel, which has support for all PostgreSQL data types, statistics collection for faster queries, and it's simple. You load the extension, you create your own table, and you update it, and then you get the PostgreSQL benefits. So that's all that I have. Thank you.
you missed a possible